Welcome to the second lecture in our course on stochastic processes. Last time we did something introductory. For example, we dealt with how stochastic processes can be equal. And today and in the next lecture, we will have two basic examples of stochastic processes. In this video, we will cover the Poisson process, and in the next video, the Brownian motion. The Poisson process is something, rather simple. It's called Poisson process because at any point in time t, it has a Poisson distribution. So let's get started. So the Poisson process. So let's of course start with the definition. And before I start with the definition, I tell you what the Poisson process is about. What do we want to do with this? The Poisson process is a count process, which means it takes values in 0, 1, 2, and so on because we're counting something. It has independent increments, which means if I have 3 points in time actually, then I have the increment between the first two and the last two, and they are independent. And that should hold for any number of increments, so any number of different time stretches. So they're independent. It should also be that their distribution, so the distribution of the increment, so what happens between these two time points, depends only on the length. And I formulate this here. The difference in the values is the same as the difference between the value at t2 minus t1 and 0. And the third thing, no double points. So between x epsilon and x0, it's very unlikely that we have a jump of more than 1. Let me just go to the last slide because I can show you a picture here. So let's only focus on the left picture here. So that's what a path of this process looks like. It waits, and then there's a jump. It jumps up 1, another 1, and so on. And that fulfills apparently what we wanted to do in some sense. So it counts something because at any point in time t, I have a number which I could call a count. It only increases, which means more events happen, and the events are these dots here at these times. Well, there's a chance that it's only a very small time stretch such that the next event comes, but still it's a time stretch, so the last property also holds. And of course the independence here you cannot really see because that's something on the distribution and you only see one single path here. So that's the Poisson process, what we want to do. That's how we define it. X is a Poisson point process, or PPP, with an intensity lambda. The family increments are independent as we wanted it. And increments are Poisson distributed. And we are actually going to show that this is a consequence of the first three properties. So the Poisson distribution is a consequence of what we wanted to model here. So first, let's say there's exactly one Poisson point process. And depending on how you understand it, that's a true or a false claim. So I tell you what I mean by this. I mean by this that there's only one probability distribution on the set of paths from the positive real line to R, such that the distribution satisfies these things here. So being a Poisson process or not is a distributional property. So that means we need to define the distribution. Why is it unique? Well, it is unique because we uniquely determined the finite dimensional distributions, and as we discussed last time, where is it? Here, x equals y in distribution if they have the same finite dimensional distributions. So there we have uniqueness. And for existence, as we discussed also last time, we need a projective limit of things. So we need to define the finite dimensional distributions and see that they form a projective family. Well, and the most important thing by this, please recall that if you have a Poisson process with parameter alpha and you make the convolution with a Poisson process with Poisson distribution with beta, there's a result which is Poisson alpha plus beta. So that's important for this projective property here, actually. Because, let me draw something. If I have 3 time points, t1, t2, and t3, the increment between t1 and t3 is Poisson t3 minus t1, and that's the same as the convolution of the increment between t1 and t2 and between t2 and t3. Here's the reason. And that means if I have the 3-dimensional distribution and I project onto the 2-dimensional distribution, it's the same. That's the projective property. So formally, what do I have to do? I have a J, a finite index set in my index set. I have to define the finite dimensional distributions. And what's that? Well, I take these Poisson increments here and I make the convolution. So, well, if I have the increments, apparently, if I have the increments, I can as well compute the states by themselves by just summing up. So, for example, in order to get to xn, so x0 should be 0 here. In order to get to xn, I only have to sum up all these things. And because I'm summing them up, I'm getting a convolution of distributions. And, well, by this property, which I also recall here, I have the projective property, which means the Poisson point process exists in the sense its distribution exists. Okay, that's for starters. Then let's come to some properties. Here is the proposition, which I also mentioned, which shows that these 3 properties essentially determine uniquely the Poisson point process. So X is a non-decreasing process, it starts at 0, has values inside plus. This is a Poisson point process with parameter lambda if and only if. Well, lambda should better be the expectation of x1 minus x0 because the Poisson distribution has an expectation which equals its parameter. And 1 to 3 from remark and so on hold. And of course, there are 2 things we have to prove, from left to right and from right to left. So we have a Poisson distribution, so we have from left to right, and 1 to 3 should hold. Independent increments, okay. Identity distributed increments, okay, by definition. That's just by definition. The only thing we have to check is these no double points here. So 1 and 2 are okay. For 3, let's check the double point property. And just going back here, x0 is 0. So I'm writing down this here. I have to compute the limit of this here. And I cannot do that because I know how x epsilon is distributed. The probability that a Poisson distribution has more than, is greater than 1 is 1 minus the probability at 0, 1 minus lambda epsilon minus the property it's 1. That's lambda epsilon times e to the minus lambda epsilon. And, well, maybe one thing would be to see the exponential series. If epsilon is small, then this here is basically 1 minus the parameter plus, well, parameter squared times some factor. Well, I can also transform this a little bit in order to really get a nice thing. 1 minus e to the minus lambda epsilon times 1 plus lambda epsilon, like this here. And well, wait, what happens here with my pen? This here is bigger or equal than 1 minus lambda epsilon. Because it carries a minus sign, I can bound from above by 1 minus lambda epsilon times 1 plus lambda epsilon, which is, well, you can compute this lambda square epsilon square. Yeah, lambda square epsilon square divided by lambda, so that's lambda square epsilon, which of course goes to 0 as epsilon goes to 0. And we have proved the third property. So the other way around, the other way around. So now from right to left. So I start with the three properties and I have to come to the definition of the Poisson process. So the first property, independent increments, well, that's the same as the first one here. So from right to left, first property is okay. We have to show that xt has a Poisson distribution with parameter lambda t. Then we are basically done. Why is that? So from this we need to have that we have the Poisson distribution, because then this here is immediate. Because it only depends on the time difference. That's basically what we should prove. So I'm making an approximation with small time steps. So that's the basic point. Set k to the n. And assume n is large. And k is smaller or equal to n. So that's tk divided by n minus xt k minus 1 divided by n, minimum 1. And let's also say xt to the n, that's the sum over set k to the n, k from 1 to n. And the interesting thing here is that I know the distribution of xt to the n, because between such two time points, tk minus 1 divided by n and tk divided by n, just two things can happen. There is an event, then this thing here is 1. If there is more than one event, it's also 1 because I make the minimum with 1 here. Or there is no event, and then that's 0. So here is a sum of 0 ones The 0, 1s are independent because of the independent increments. And that means the xt to n is binomially distributed with parameter n and probability that xt divided by n is bigger than 0. Like this. So that should be an n here. And we are just going to use the usual approximation of the binomial by the Poisson distribution, because we have to show that something is Poisson. Well, of course, in n, these things here are increasing, because xt makes some events, and I only do not count one event if it's in the same interval tk over n and tk minus 1 over n as another event, and that becomes rarer and rarer, with the effect that this here is increasing. And we have the probability that the limit of n goes to infinity, xt to the n, is not equal to xt. So what must happen? Well, some event, so it's monotone first of all, which means I can exchange the limit and the probability. T to the n is not equal xt. That's smaller or equal than limit n goes to infinity. Well, when are they not equal? They're not equal if I have one of these time intervals where I really have to cut it in one. So times times the probability that xtk over n minus xtk minus 1 over n is bigger than 1. And I'm summing here from 1 to n. Because of the identical distribution, that's the same as n times this probability, x times n times probability that the increment, which has the same distribution, t over n, bigger than 1. And that here, because we have the third property here, no double points, goes to 0. This here is 0. So x sub n and x will be the same as n goes to infinity. That's one thing. And for this reason, we have, for example, lambda t is the expectation of xt by assumption. Yes, by this assumption here. And that must be, by monotonicity again, the expectation of xt sub n goes to infinity. No. And this here is as we just saw, n times n times the probability that xt over n equals 1. That's bigger than 1. Doesn't matter. So which is, let's write it correctly, bigger than 0. Like this here. And this binomial distribution here, we know, converges to the Poisson. So Poisson approximation. You can look that up in the course on probability theory. We have that the probability that xt equals k must then be that the same as the limit that probability xt to the n equals k as n goes to infinity. So that has the binomial distribution, which converges to the Poisson. So the result is that's Poisson with parameter lambda t of k. And we have shown that xt must have a Poisson distribution. And we have shown everything. Yeah, because what we wanted to show that we start with 1 to 3 and we want to show it's Poisson process, and that's what we just did. Then there is a special construction of the Poisson point process. And I show you this maybe along this picture here. So, how they call S? Okay. Let's call this here S1. That's the waiting time until the first event happens. This here is maybe the waiting time S2 for the second event. S3 is very small. Here I have S4 for the fourth event and so on. And the question is, how are they distributed? So what's the distribution of the waiting time? And can I use the waiting times to construct my process? And the answer is here. The waiting times I consider are exponential distributed, IID, with parameter lambda. And x is given by, well, xt, well, I write it like this here, the maximum I such that S1 plus and so on plus is I smaller than t. So for example, if my t is here, the state is the largest index such that S1 plus S2 plus S3 is smaller than t. Well, that's 3. The index must be 3. It cannot be 4 because when I do plus S4, I'm here, I'm bigger than t. So the state is 3. Then the claim is X is a Poisson point process. And let me try to compute this. Xt equals k when I do this. That's only a special case because I'm only computing something about the one-dimensional distributions here. I would have to do that for all finite-dimensional distributions, but the calculation is already rather long. So I'm doing this here. What's the probability that xt equals k using this construction? So what do I need? So here I have my t. I need k points here, which, k points here such that S1 plus S2 and so on plus Sk is smaller than t. And then when I add the k plus first waiting time, it's bigger than t. So, the first exponential distribution has lambda e to the minus t, e to the minus lambda t1, that's the first one. Then the second has time lambda e to the minus lambda t2 minus t1, where t2 is somewhere between t1 and t. And so on. Then I have lambda e to the minus lambda tk minus 1. Yes, and that goes here from, so that determines my tk, which goes from tk minus 1 until t. And then for the k plus first, the k plus first needs to be larger than t minus tk. And the probability for that is e to the minus lambda t minus tk. And I have to integrate over all tk until dt1. So that's this probability here. Let me rewrite that. I have k lambdas here, so I have a lambda to the power of k. And something nice happens with the e to the power of something. I have here e to the minus lambda t minus tk, then tk minus tk minus 1. So that tk here goes, that tk minus 1 goes with the next one, and so on. And the t1 goes also. That means I have e to the power minus lambda t in front of the whole thing. And essentially nothing remains in the integral. 0 to t, t1 to t, and so on, tk minus 1 to t, dtk, dt1. And let me do something, well, it looks a bit stupid. I'm saying t to the power of k divided by t to the power of k. Why am I doing this? Because this here, with the numerator and the integral, I can interpret as a probability. So let's say u I is uniformly distributed on the interval 0 to t. So it has the density 1 over t dt. And here, I can write it here as the probability that u1 smaller than and so on smaller than uk. Because the ui's here, well, they should be increasing in order, so that's exactly this here. And the probability for this, because the order is any order, and there are k factorial orders of this, I end up saying, well, that's lambda t to the power of k, e to the minus lambda t, divided by the probability, which is k factorial. So that's exactly the Poisson distribution at time t. So I have now shown, using this construction here, I recover the Poisson distribution. So it's something to remember. In the Poisson process, the waiting times to the next event are exponential distributions. Yes. And with this slide here, I want to make a last remark, which is something connected to the last lecture, where we dealt with modifications of stochastic processes, because the question is the event here such that the path is right continuous, or is the event here such that the path is left continuous? Well, both are valid options at first start. But as we will see, there are reasons to choose the left one over the right one. But I'm only going to say here, the two processes here, the left continuous Poisson process, this one here, and the right continuous Poisson process, they are modifications. Because if I fix some t, the probability that you hit an event here is 0, which means that the probability that the right continuous and left continuous Poisson processes are the same as 1, and that means they're modifications. Let me also briefly mention why we will favor the right continuous version over the left continuous one. The reason is that in the left continuous version here, for example, if you're here, well, you immediately jump. So in order to say what's the future of this point here, you would have to look into the future a little bit, because you know it immediately jumps. And that's not the case here, because if you're at this time point here, well, you know, it just continues to be like that. You do not have to look into the future. But this looking into the future and stuff, that's something we have to formalize in later videos, I guess, and maybe that's not even the point of this lecture, that's more for the next lecture. So that's it what I wanted to say about the Poisson point process, and next time we will deal with Brownian motion. Hope to see you there.